Welcome to Mrs. Z's Chemistry. In this lesson, we are going to learn how to calculate pH. This is the third lesson in Chapter 14, Acids and Bases. So pH is defined as the negative base 10 log of the concentration of the hydrogen ion, and it has this equation. Even if you have not learned logarithms yet in math, this will be super simple because all you need to do is press a specific button on your calculator. Because the equation has the negative sign in it, you need to first press the negative button, not the minus sign. So this is usually where it is on the different calculators. And then you would press the log button. As you can see if you can find the log button on your calculator. And then you would type in the concentration of the hydrogen ions. And then you can close the parentheses and press enter, and that is the pH. We have seen so far this equation where Kw is equal to the concentration of H3O times the concentration of hydroxide, and that is equal to 1 times 10 to the negative 14. In pure water, the concentrations of H3O plus and OH minus are equal to each other. So then you can see that the concentration of H3O in pure water is 1 times 10 to the negative 7. So type into your calculator to find the pH of water when you have this equation. pH is equal to the negative log. So type this into your calculator, the negative sign, the log button, and then 1 times 10 to the negative 7, close the parentheses and press enter, and your calculator should give you 7, just like this. An acid has a higher concentration of H3O than hydroxide, and it's higher than in pure water, so its pH is less than 7. And then a basic solution has a lower concentration of H3O than in pure water, and it's a higher concentration of hydroxide, so its pH is greater than 7. Another way to look at it is like this. Acidic solutions have an H3O concentration greater than the hydroxide ion concentration, and the pH is less than 7. Neutral, like pure water, the H3O is equal to the OH, and pH is equal to 7. In a basic solution, the H3O is less than the hydroxide amount or concentration, and the pH is greater than 7. This right here where it says the pH at 25 degrees Celsius, that is only because the Kw changes at different temperatures, but in this class we are only going to look at problems that are at 25 degrees Celsius, so you don't need to concern yourself about changing the temperature or changing the Kw value. So what's interesting is that the P in pH just means to take the negative log of the thing that comes next. So in this case, the H, which it would be the hydrogen ions. But pOH would be to take the negative log of hydroxide concentration. pKw would be to take the negative log of the Kw. So that would be negative log of 1 times 10 to the negative 14, which equals 14. That is what pKw equals. We'll learn later what a Ka is, but if you were to take the negative log of Ka, then you would get pKa. So here's a nice chart showing the hydrogen ions, written as H+, the pH, the pOH, and the hydroxide of some solutions. On the left-hand side over here, we have some examples of acidic solutions. Stomach acid is very acidic with a concentration of 1 times 10 to the negative 1. That means its pH is 1. The hydroxide level concentration is really low in stomach acid. It's only 1 times 10 to the negative 13. Therefore, the pOH is 13. The pH and pOH are inversely related to each other, and H plus and OH minus are inversely related to each other. Lemon juice, soda, vinegar, wine, tomatoes, black coffee, rain, saliva, and even milk. These are all examples of acidic solutions. Most of the foods and drinks that we consume are acidic. They have pH less than 7. Over here, we have some examples of basic solutions. Human blood is about 7.4 pH, just slightly basic. Seawater, borax, lime water, and household ammonia and bleach and other cleaning products and detergents are basic. Remember that hydronium ion means hydrogen ion, and it could be written as either H plus or H3O plus. Therefore, the equation for pH could be written as either negative log of H plus or negative log of H3O plus. Just don't get confused. Those are interchangeable. So let's do some practice problems. If a solution has an H3O plus concentration of 1.5 times 10 to the negative 6, what is the pH of the solution? And is this acidic or basic? So in order to calculate this, we need to take the negative log of the H3O plus concentration, which is the 1.5 times 10 to the negative 6. And when we do this, we get an answer of 5.82. This is below 7 on the pH scale, so this is an acidic solution. Now let's go ahead and solve the next one. If a solution has a hydroxide ion concentration of 8.5 times 10 to the negative 2, what is the pOH of the solution? And is this basic or acidic? Pause to see if you can work this out. So the answer, the pOH is 1.07, and on the pOH scale, the lower the number, the more basic the solution. As you can see, let's go back up to our chart. We had a pOH of 1.07, which is about right here. So therefore, it's very basic down here. If we had a pH of 1.07, that would be up here, and that would be acidic, but we don't. We have a pOH, so it's a complete opposite scale. All right, you're not going to know how to do this math, but I'm going to show you how we can derive an equation to get a new one. So we have seen this equation here, H3O times OH is equal to KW, and that is equal to 1 times 10 to the negative 14. If we take the negative log of both sides, we then get this. Negative log of H3O plus negative log of OH is equal to negative log of KW, which is equal to 14. Now, if you notice, this equation right here is also equal to pH. And this equation, negative log of hydroxide, is equal to pOH. And negative log of KW is equal to pKW, which is 14. You don't need to know how to find this equation or how to derive all of that math. You just need to notice that this equation right here is on the back of your periodic table. pH plus pOH of any one solution is equal to 14. So here are all of the equations that you have on the back of your periodic table. pH is equal to the negative log of H3O plus, and in order to find the H3O plus concentration, then you take 10 to the negative pH, and that's going to equal H3O. Same with pOH is equal to the negative log of hydroxide. If you want to find the hydroxide concentration using pOH, then you take 10 to the negative pOH, and that equals your hydroxide concentration. Also, we have pH plus pOH is equal to 14. All of these equations are on the back of your periodic table, and we will be using all of them in the practice problems here. So let's do a few problems. If a solution has a pH of 5.63, find the H3O plus. So we want to find an equation that we can isolate H3O on one side, because that's what we're trying to find, and we're going to use the pH. Now, there's lots of equations that have H3O in it, but we want to find one where we get to use pH in the calculation. Here's the answer to the first part. 10 to the negative pH is equal to H3O. So 10 to the negative 5.63 gets us 2.34 times 10 to the negative 6, and that is the molarity or concentration of H3O. Pause to see if you can solve the next problem. And here's the answer. pH is equal to the negative log of H3O. H3O is what we're given, so if we plug that into the negative log, we get 3.25, and that is the pH. pH does not have any units. Now let's solve the last one. If the pOH of a solution is 3.49, what is the pH? So we're given pOH, and we're trying to solve pH. There's lots of equations with both of these, but which one has only these two in the equation? pH plus pOH is equal to 14. Therefore, 14 minus pOH, which is the 3.49, equals 10.51. And that is the pH in this problem. So we have 7 strong acids on the back of our periodic table. And these are, by definition, strong electrolytes, which means they exist completely as ions. All of the reactants turn into products. They are completely dissociated. So any strong acid concentration is equal to the concentration of H3O plus. Our strong bases are any hydroxide with an alkali metal. The alkali metals are the Elements in the first column of the periodic table: lithium, sodium, potassium, rubidium, cesium, francium. Any of those with hydroxide, like LiOH, lithium hydroxide, or NaOH, sodium hydroxide, any of those are strong bases, and the concentration of your strong base is equal to the concentration of hydroxide. We also have a few more strong bases, and that is the heavier alkaline earth metals. Alkaline earth metals are the second column. The heavier ones are calcium, strontium, and barium. These three right here. So those three elements with hydroxide are also strong bases. We just need to remember that because they have a 2+ charge, they each have 2 hydroxides. So you double the concentration of any of these particular 3 strong bases, and that'll get you the concentration of hydroxide. And we'll look at a sample problem later on that involves calcium hydroxide. Here is one more problem, or another problem here. Find the pH of a 0.05 molarity solution of HCl. Pause to see if you can work this out. HCl is a strong acid, and we know that because it is on our strong acid list. Therefore, the concentration of HCl equals the concentration of H3O. Therefore, in this problem, H3O is 0.05. Take the negative log of that, and we have a pH of 1.3. Find the pH of a 0.1 molarity solution of NaOH. Pause to see if you can work this one out. NaOH is a strong base. Therefore, NaOH concentration is equal to the OH concentration, which is equal to 0.1 molarity in this problem. When you take the negative log of 0.1, we get pOH. And the pOH of this solution is 1. But the problem is asking for us to find the pH of this solution. So then you need to use one more step in order to solve for pH. So therefore, the pH of this problem is 13, which makes sense because a very high pH, this is very basic, and this would make sense for a strong base, which sodium hydroxide is. All right, now we're going to do one more problem here. Find the pH of a 0.1 molarity solution of calcium hydroxide. Pause to see if you can work this one out. So calcium hydroxide is a strong base, and when it dissociates, we get 2 hydroxides for every 1 calcium hydroxide. I like to use the analogy of an Oreo cookie. This is my Oreo cookie. When I break apart my Oreo cookie, I have 1 cream filling and 2 chocolate cookies. If I were to have 2 Oreo cookies and break them apart, I would end up with 2 cream fillings and 4 chocolate cookies. It's just a ratio of 1 to 1 to 2. So when I have 0.1 molarity from the problem of calcium hydroxide, that means I have 0.1 molarity of calcium ions, which I don't really care about in this problem, and then double that, 0.2 molarity of hydroxide ion concentrations, hydroxide ions. So when you take the negative log of this, that gets us pOH, and that's 0.70 is the pOH. Subtract that from 14, and this problem has a pH of 13.3.